Hello, ladies and gentlemen. Root Beer here, and we're looking at the 2008 Hypatia, and we're on the very last question, question number 4. This should be the hardest question on the paper, so hopefully you've given it a try. Even if you're just able to do part A, hey, that's great, and it's great practice that you've done that. Okay, so let's take a look at question number 4 together. The Hypatia, it's not capitalized, so I don't think it's someone's name, so maybe it's not a problem if I don't pronounce it. The Hypatia sum of a sequence, A1, A2, A3, all the way up to AN, is formed by adding the products of all the pairs of distinct terms in the sequence. For example, the Hypatia sum of the sequence A1, A2, A3, A4 is A1, A2 plus A1, A3 plus A1, A4 plus A2, A3 plus A2, A4 plus A3, A4. All right. So that's an interesting concept. I don't think I've seen anything exactly like that. I'll tell you what this puts me in mind of. These A1, A2s times A1, A3s. It makes me think of the expansion of A1 plus A2 plus A3 plus A4 squared. That's A1 squared plus 2A1 A2 plus A2 squared plus 2. You'll get twice, so you'll get the sum of all the squares. If you go ahead, I don't want to waste time writing everything out, but you will get the squares of each of these terms, but then you'll also get twice the Hypatia sum. So I don't know if that's going to be relevant, but that is something that I notice, and that's really the only place I've seen the Hypatia sum, as they call it, come up. I mean, I've never heard anything like that called the Hypatia sum, but there we go. So that's the only thing that really pops into my head right now, and we'll see if that might be useful. So A part, the Hypatia sum of the sequence 2, 3x, 2x is -7. Determine the possible values of x. So to say possible values, let's think about it for a second. At some point, x is going to be multiplied by 2x in our sum. That will give us something with x squared, so I imagine we're sort of having to solve a quadratic here. Well, we have 4 terms in this sequence, and they explicitly gave us the Hypatia sum of a 4-term sequence, so we can even just apply that formula. I like to start off each of these questions on a fresh piece of page, so I know we had a lot of paper left over from the previous question, but it's digital, so it's okay if I waste a sheet. 2, 3x, 2x. So we know it's the product of 2 times 3 plus 2 times x. I'm just going to do 2 and then everything, and then 3 and then everything, and then x, then, well, everything, but that's 2x that's left at that point. 2 times 2x plus 3 times x plus 3 times 2x plus x times 2x, and they tell us this is -7. So 6 plus 2x plus 4x plus 3x plus 6x plus 2x squared is equal to -7. I'm going to bring the -7 over. We'll have 13, and then 2, 4, 3, that's 9, plus 6, that's 15, so 15x. And then plus 2x squared is equal to 0. Okay. There's probably a way to factor this, but I'm not so good when it comes to factoring when there's a number other than 1 there. So when in doubt, quadratic formula. So -b plus or minus the square root of b squared minus 4ac all over 2a. So that's -15 plus or minus the square root of 4 times 13 is 52, because there's 52 decks in a card, 4 suits, 13 cards in each suit. And then 2 times 52 is 104. And then subtract off the 100, we get 125. Subtract off the 4, we get 121. So x is negative 15 plus or minus 11 over 4. So that's negative 4 over 4, so negative 1, or negative 26 over 4, so negative 13 over 2. Okay, I don't feel so bad that it didn't exactly multiply out, but I guess if you're really good at factoring, and some of you out there might be, you'll get 13 plus 2x, and then 1 plus x. Okay, so those are our two values for x. Maybe put a little sentence at the end, maybe a therefore statement, maybe just box them up. But we've got part A there. Okay, not so bad, not so bad. Now it's B or C, B and or C. No, it's just, it might be B, it's definitely C, that this concept really going to ramp up in difficulty. So maybe we'll read these two together. So B, a sequence has 100 terms. Of these terms, m are equal to 1 and n are equal to negative 1. The rest of the 100 terms are equal to 2. Determine, in terms of m and n, the number of pairs of distinct terms that have a product of 1. Okay. And C part C seems to start off the same way. A sequence has 100 terms, with each term equal to either 2 or negative 1. Very similar to the setup in B, we just have we'll have m equals 0, I guess. Determine with justification the minimum possible Paesi sum of the sequence. So ultimately our goal is minimize the sum. And I'm wondering, this is just a thought, just off the top of my head, based off what I said before, that I recognize the pairs of products coming from squaring the sum of four-term sequence. You get squares plus twice the Paesi sum. I'm wondering if perhaps we need to make that connection, make the sum of the sequence equal to 0. Then you square it, you'll get a whole bunch of positive things from the 2's and negative 1's being squared, plus 2 times, and then as big as possible, the biggest possible negative Paesi sum there. That's what I'm thinking. I don't know. It doesn't really look like B has a connection here, because B isn't talking about minimum possible Paesi sums. But I don't know. All right, so we'll focus on B, because I think that one's at least a little more achievable. So m of the terms are equal to 1, n of them are equal to minus 1, the rest of the terms are equal to 2. So there's really only, there are only three possibilities. Actually, no, it's four possibilities, I guess. For the term AI, AJ in the Paesi sum. Okay. Because these terms can only be 1's or negative 1's or 2's, so products of them can only be certain things. So it can either be 1 times 1 equals 1, or it can be 1 times negative 1 equals negative 1, or negative 1 times 1 is equal to negative 1, negative 1 times negative 1 is equal to 1, or we can get 2 times negative 1 is equal to negative 2, 2 times 1 is equal to 2, 1 times 2 is equal to 2, and negative 1 times 2 is equal to negative 2. And am I missing anything? Oh, yes, of course. 2 times 2 is equal to 4. So I was wrong once again. There are 5 possibilities. Okay, we've listed out all the possible things we could have, and we take note that the ones that have a product of 1 will only come about from a -1 times a -1 and a +1 times a +1. And they were just asking about 1, not -1 as well, correct? The number of pairs of distinct terms that have a product of of 1. Okay, just 1. So we only get 1 if AI is equal to AJ, which is equal to 1, or AI equals AJ equal -1. Okay. So how many pairs are there that give us 1? Well, we know there are m terms that are equal to 1. Okay? For example, if we had m as 3, we'd have 3 different 1s. Well, we want all possible pairs, so we sort of need to pick out 2 of these and take their product, or maybe it's these 2, that sort of thing. So when we're doing this, we can either use choose notation, in case you know that sort of stuff, but and your answer is going to be m choose 2. Not particularly descriptive, but if you know this notation, you likely know that it means this. And that's all well and good, but that's not always part of the high school curriculum everywhere. So let's see how we would do it if we didn't know binomial notation, if we didn't know choose notation and combinatorics and all that stuff. Okay. So to make a product of 1, pick 1 AI of these m terms. Okay. There are m possible choices for I. Once this one's chosen, this leaves m minus 1 other terms in the sequence. To choose for AJ equal to 1. Okay? So there are m times m minus 1 ways to choose our product. However, if you were to say, let our sequence not have 100 terms, but let's say 3 terms, and all of them were equal to 1, you would get products like A1, A2. We chose 1, and then we chose 2. Or we chose 1, and then we chose 3. Or we chose 2, and then we chose 1. And uh-oh, these 2 are the same. And remember the definition of a Paesi sum. It's the product by adding all the products of distinct terms. Okay? Notice that they don't have A1, A2, and then somewhere else down the line they have A2, A1. As soon as you've chosen the pair 1 and 2, you get just one product for that. So we might say, notice, however, that we are double counting. Choosing I equals 1, and then J equal 2, is the same product, or same term, as choosing I equals 2, and J equals 1. Okay? So my argument that I'm going to be making is, okay, there's 2 ways to get each product, so we'll divide our m times m minus 1 by 2. You can avoid this from the start by saying, okay, we'll make it so that all our products of 1 times 1 go in order, just like they have listed. They have A1, A2, A1, A3, A1, A4. So you could say we can pick any of these I, or any of these M products or M terms for our first thing. And then the second one we choose will have to have a bigger index. Okay? And that will avoid this double counting. But that's a little harder to get a formula for, just trying to think through it. Okay? It's not impossible, but it's a little harder to work one. So I'd rather, naively count everything up by M times M minus 1, just rather sillily isn't a word, in a rather silly manner, just throwing all the terms together no matter what order, and then realizing, oh, I happen to have counted everything twice, let's just divide by 2. Not saying that doing it the other way is bad, I just find this a little easier to explain. So I'll even say the product is A1, A2. Okay? So, there are, in fact, it was M times M minus 1 over 2 products of the form 1 times 1. Okay. Similarly, there are N times N minus 1 over 2 products of the form -1 times -1. Thus, in total, there are M times M minus 1 over 2 plus N times N minus 1 over 2 products having the value 1. Now, I feel right now like I'm missing something because they made it very clear we said a sequence has 100 terms. And I didn't use that anywhere. So determine in terms of M and N the number of pairs of distinct terms that have a product of 1. Well, I didn't use the 100. All I needed to know was, suppose we have a sequence, M of the terms are equal to 1, and N of the terms are equal to -1, and all the others are equal to 2. That's all we really needed. Why did they give us 100 terms? Maybe there's a connection with C, but really they would have probably started with a sequence has S terms, and then it's up to us to make S equal to 100. I don't know. It seems odd, and it makes me feel like I missed something that I didn't read B carefully enough. But I reread it. It seems fine, so we move on to C. Sequence has 100 terms, with each term equal to either 2 or -1. Determine with justification the minimum possible Paesi sum of the sequence. So I already said I think I have an attack plan for this. And right now I can't see a way to use B exactly. It's not really coalescing in my head there. But I think if I use what I said before, which was just a sort of a throwaway connection, I honestly didn't think it would come up here, but I think... So this is what we're going to have. We're going to... So let A1, A2, A100 be the sequence, or be such a sequence. Okay, and then we'll minimize it. But we'll say such a sequence so that we have those -1s and 2s here. Okay, I think we're going to have to sort of split it. A third of these will be 2s, and then the remaining amount will be -1s, or something like that. But of course, there isn't a clean split, so it might be a bit more of a challenge. If this were 99, I think we'd be all set. 33 of them are 2s, 66 of them are -1s. Alright, but I'm going to connect it back to my observation at the start. A1 plus A2 plus A100 squared is equal to a1 squared plus a2 squared plus a100 squared plus twice Paese sum. Okay? If you wanted to, as an intermediate step, instead write the plus 2a1a2 plus 2a1a3, yada yada yada, and then restate this, but I don't think it's necessary. I think just state that this is how the formula works. If you want to, do an example really quickly, but there we go. So we got all the squares plus twice the Paese sum. All right. Now, we want to minimize the Paese sum. And it's weird that they use the word minimum. Because I think we can make this term negative, and so I guess minimum's better than smallest. Okay. I think I'm just a bit too much in my head when I'm trying to do this particular question right now. But that's okay. We'll soldier on. Not everyone has a perfect day. Okay. Least of all when you're on when you're doing a contest for real. All right. So each of these fellas is positive. Well, I shouldn't say positive. If they were all 0, no, they're definitely positive. And this giant thing here, because it's squared, I can say it's non-negative. Okay? So I want to minimize my Paese sum. And I want to use this in some way. Well, I'll tell you what. Only what was it? They didn't tell us how many. I'm going to say let n be number of terms with ai equal to -1. Okay? Then I know that 100 minus n of the terms are equal to 2. So I can change these expressions. I can make it n times -1 plus 100 minus n times 2 squared. And then we'll get n copies of -1 squared plus 100 minus n copies of 2 squared plus twice the Paese sum. Okay. So I can simplify this. This is 200 minus 3n squared is n plus 400 minus 4n plus twice Paese sum. And I can expand over here. 40,000 minus 1200 n plus n squared. And we'll get a parabola, I think. Oh, we could get a parabola and then maybe put it in vertex form. And the vertex will be where the minimum is. Maybe that'll work. Plus n squared is equal to, and then I cannot remember what it was that we had on the other side. 400 minus 3n plus twice the Paese sum. I'm going to say let p, just so I don't have to keep writing the Paese sum. Okay, let's do some rearranging. So n squared We bring the 3n over, which is laughable, and again makes me think that I've done something a little wrong. Plus, subtract off 400 here, so we'll get 39600 minus twice the Paesi sum is equal to 0. Alrighty. Well, I suppose we complete the square. Except this isn't... It's not even, so I'm going to have to do something a little bit more. And because of that, I just want to double check. Minus n minus 2n, so it's 200 minus 3n, it really is. This isn't n squared, it's 9n. Not that that especially helps us, but it's 9n squared. And 400 minus 4n, and then regular n, so 400 minus 3n. And 3 times 2 times another 2 is 12. Okay. So put the 9 back in here, and the 9 back in here. These guys... I can take out factor of 9. I'm going to grab my calculator just to make this quick. So minus 133n plus, and then 396 divided by 9, 4400. And I'm going to leave off the 2p. I don't know what to do with it. I don't think I can take off a factor of 9 there. I mean, I suppose I have to. So, but anyway, I guess we'll have to do 133 divided by 2, which is going to be so we'll add on 133 over 2 squared, and then subtract off 133 over 2 squared. And what is that when I square that out? So 9n squared, 133n, plus 4422.25, minus 4422.25, plus 4400, minus 2p is equal to 0. And then... so we get 9n minus 133 over 2 squared. And so that takes care of this, and this. And then these guys cancel out. The 44s will cancel out. So we'll just get negative 22.25. Multiply that by 9 to bring it on the outside, and we'll get 200.25 minus 2p is equal to 0. Alright. So I want to make my Paesi sum as small as possible, and this has to be true in the relationship between n and my Paesi sum. So to make my Paesi sum as small as possible, I will rearrange and have it be like this. Now, to minimize p, the Paesi sum, we must minimize the right-hand side parabola. Okay, but there might be an issue here in that if I put I might not be able to. I don't think I can make p equal to 0. That's what I'm trying to get at here. Oh, also this should be minus. It should be minus. Now, to minimize 9n minus 133 over 2 squared minus 200.25, we just need to minimize n minus 133 over 2. That's the only thing we really have control over here. Okay, but n must be a positive integer. Sorry, we want to minimize the square. So we want to minimize the positive integer. To minimize this means to get as close to 0 as possible. So n being equal to, so 133 over 2 is 66.5. So we want n to approximately be 66.5. So we could try n equals 66 or n equals 67. And hey, that's sort of what I called earlier, because I think if it's 99, this will turn into n minus 66 plus something or other. So that's sort of what I was saying earlier. Nifty. I didn't actually know whether or not that would all work out. But either one of these will be only off by a half. So n minus 133 over 2 squared will be equal to a half squared. So it'll be equal to 1/4. And then 9 times 1/4 minus, what is that, 200.25 really? It's 801 over 4. So this is 9 minus 801 all over 4. And I really hope this works out and gives me an integer. And it does. I mean, it kind of has to. As long as I chose n as an integer, the relationship I built up would force it to have to be an integer when I spit this out. We'll break it down into one more step. It's negative 792 on top, and then we get negative 198 on the bottom. Okay, so that tells me that negative 99 is equal to p is the minimum possible Hypatia sum. Okay, and it is achieved. We don't need to add this, but I will point it out. It is achieved when there are exactly 66 or 67 minus 1s in the sequence. Okay. So, I think that one went a lot faster and a lot smoother because I sort of made that connection. I asked myself where. I didn't even ask myself where have I seen this before because I didn't know I'd seen it somewhere before. But just as I was reasoning it out, it's just, oh, I made that connection. It's the sum of all possible pairs, just like the sum of all possible products of triples. I would think cubes, that sort of thing. But cubes would be a lot messier if you had to base the question on that. But because I noticed that, I think this whole question 4 went a lot faster and a lot smoother. I did get a little stuck here when I was fiddling around with the parabola. So I learned pretty quickly that I couldn't just split it into a third of them 2s and a 2/3 of them -1s. That wouldn't work. But I think the same sort of analysis would prove that if you had 99 terms, I'd be correct. Anyway, yeah, I was a little hesitant when we saw this 1197, but fortunately the 9 factored out, and it wasn't so bad. I mean, it wasn't to the point in terms of, sometimes you get a sense when you do these calculations, you realize, gee, I'm not doing this the right way, just because there are so many awkward numbers and the equations are getting so long. I never really felt like that here, but had the 1197 turned into something even worse, I probably would have said, whoa, hold on, maybe my initial thought didn't work out quite right. Okay. Once I got the parabola, I moved the Piazzi sum over to the other side, and we just minimized that parabola as much as we could, remembering that n's got to be an integer. So you wouldn't say, I could see someone falling at the very last hurdle saying, oh, the minimum must be 200.25, neglecting the fact that the Piazzi sum has to be an integer. But yeah, smooth sailing, and I think that went a lot faster than most of my Hypatia 4s tend to. But yeah, I'd say it was a good overall 2008 paper. I look forward to the 2009. I also look forward to the 2008 Euclid, which will be the next contest that I plan to record and upload. So if you guys are itching for more written contests, by all means, join me for the 2008 Euclid. If you're looking for more Hypatias, those will be up, and of course I have a bunch of other ones. If you're looking for more grade 11 content, of course, you can try the multiple choice contests, the Fermat papers. And yeah, thank you guys for watching. Feel free to like or subscribe, and I will see you in a future math video, whatever it may be. Until then.